These little TFT screens are great add-ons to your Arduino. So let's see what we can actually do with it. Hi and welcome to Bytes and Bits. If you followed my last video tutorial on setting up one of these little SPI LCD screens, you'll have been able to get that up and running, and you'll have used the demo software from the Adafruit libraries to get something happening on the screen. But now that we've got that far, let's see what we can actually do with it and get some animations on there. And let's have a look at both what the screen is capable of and how we have to adjust our code to create these animations correctly to make sure that we can actually get things happening at the correct speed. So let's get straight into some code and get something moving around on the screen. We'll start by just trying to get some basic graphics functions working. And the code I've got on the screen is pretty much where we left off from in my previous video on setting up the touchscreen and LCD. And I'll put a link to that up in the top corner. So really all we're doing is we're importing our libraries. We're setting up the various pins that we're going to be using. I've added in something called rotation here, so I defined a constant called rotation, and that's going to specify which orientation the screen is in. So the values here from 0 to 3, and 3 is a landscape screen mode with the pins on my TFT to the left. We're then coming down, setting up the actual hardware itself. And then we go into our loop. The only things I've added in here is I'm using one of the functions in the graphics called fill screen. That very much does what it says. It fills the screen, and you can see that I then have a constant I'm using here, which is the color definition for black. The color definitions on the ILI 9341 are a little bit more complicated to work out. They're not just straightforward RGB values. It's not a full 24-bit color. I think it's something like it's either 16-bit color or something like that. So you have to use your RGB values and translate them down in a certain bit pattern. But those have been done for you, and we'll have a look at where those definitions are in a second. What we're then doing is we're coming into our main loop. So I've set up a few sort of variables, and that's going to let me then draw a rectangle. So you can see here again I'm using one of these graphics functions, this fill rectangle. And again that's going to draw a filled in rectangle with its top left corner at coordinates x, y, and then a width and a height, and then in a particular color. But these graphics functions then, those are part of this Adafruit graphics library. And there's lots and lots of functions in there. And to work out what those are, there is a tutorial on the Adafruit website that takes you through some of the functions. But one of the best ways is to simply go and have a look and then work them out for yourself. So we need to have a look. If we look at the top here, you can see that we are importing some header files. And these header files are part of the C++ definition, where it lets us prototype or specify what functions are available within this library. So if we have a look at this header file, we should find those all listed out. So if I go across onto my computer, so again, I'm on a Windows computer, and these are stored. So if I go to my Documents folder, I should then find a folder called Arduino. Inside that, I'll find a folder called Libraries. I'll then find a folder for each of the libraries which I've imported into my system, and I want to look at the graphics library. And inside there you'll find this file Adafruit GFX.h. So again, if you're working on a Mac, I think it pretty much follows the same convention on a Mac, where it puts it in your Documents folder, and on Linux I'm sure it is something very similar as well. You just have a look on the Arduino documentation, you'll find out where it stores these files. But if I open that file up in a text editor, so I'm using the Atom text editor here, but any text editor at all will open it up. And all we're going to do is we're simply going to have a look and see what's available. So we can see there, it's just setting things up. And here we have the actual class definition, or the class prototype, which really describes to other bits of code, such as ours, what's available within this package. So we can see there's the constructor function. We then have some very sort of base level functions. So we have a draw pixel, so we can, again, here we call draw pixel. We have to give it an X and a Y coordinate. And again, these are now specifying exactly what size of integer they are. So that's a 16-bit integer variable. So X, Y, and then the color itself. And again, those colors we said there is a definition for those in one of the other header files, and we'll have a look at that in a second as well. There's then a whole load of other functions which are defined out, and you can see here we have the rotations and so on, and then we come down to some of the actual drawing functions. So this is the basic drawing API. So we can draw fast lines vertically and fast lines horizontally, and really what's happening here is that every pixel that we need to draw has to be sent across and specified on our TFT. So drawing vertical lines and horizontal lines is obviously a lot easier than drawing diagonal lines, where we have to work out where exactly the next pixel is going to be in that line. So those two versions there, if you do want to draw vertical and horizontal lines, those will create the line much faster. As we're going to see in a second, speed is of the essence on this particular type of display. We then have the one that we were using, so we were using a fill rectangle, and you can see the fill rectangle function then requires an X and Y coordinates, which are integers, a width and a height values, which again are 16-bit integers, and then again our fill color. And you can see then we've got the fill screen, the draw lines, draw rectangles, and so on. So there's a whole wide range of base graphics functions that we can use here. And the best way to work out what these do is to simply have a look at them. There's obviously some documentation available for you on the Adafruit website, but a lot of them you can see that they make sense from what they are, so setting fonts and so on. Some of these bitmap ones you will need a bit of information as to how you construct bitmaps and how you get them into your software. But again, a lot of that is available for you, or it's fairly straightforward. So I'll come back to our Arduino code then. So all I'm doing here is I am now coming in and I'm simply going to draw a rectangle on the screen. So let's upload that into our Arduino and see what actually happens with that. So there we have the code uploaded, and as it starts to boot up, we should then see that it clears the screen and we get a red square appearing. So not massively exciting at the moment, but obviously it means that we are getting it to work, and we have now accessed that particular function in our graphics library. So let's see if we can get this square moving. So to do that, I'm going to have to define some speeds in here. So we've got X and Y coordinates at the moment, but we will then need to add in an X and Y velocities. And again, I'm just using this in pixels here. Inside our loop then, we will need to do some updating and limit checking. So I'm simply then increasing my X coordinate value by the X velocity, my Y coordinate value by the Y velocity. We're then doing some limit checking. So if X has gone less than or equal to 0, that means it's gone off the left-hand edge of the screen. And all we're doing there is we're just going to then reverse its velocity, so it will start coming back onto the screen. If we then are using one of the graphics functions here, so once we've initialized our TFT screen, we'll be able to read its pixel dimensions using this value TFT width and then TFT height down here. So we know that I've used this variable here, square width. So if my X coordinate has gone greater than or equal to the width of the screen minus the width of the square, then we've gone off the right-hand edge of the screen. And again, we simply then reverse the velocity. And the same for the Y coordinates. Then we simply draw our rectangle, and that should get it moving around the screen. So at the moment then, we're not doing anything to clear the screen, so at the moment our rectangles will be drawn, but we need to clear them. And if you looked at any of the other animation code that we've been doing, perhaps with the TIC80 or my Python course, you'll see that really what we do is we clear the screen and then we draw the new screen. So let's try that on this screen as well. So I'm just going to fill the screen with black, and then we're going to draw the new rectangle. So let's upload that to our Arduino and see what actually happens. So here it comes up. We have our red square, and we can see now that it is moving, but we're getting this flickering happening. So let's see if we can work out what's actually going on here. We know that we have this function fill screen, and that actually has to write an entire screen of black pixels. And if you look at the system when it really starts up, so if I just click on the reset button here, we'll see if I reset that, you'll see that black screen comes in gradually. But that actually is it doing this fill screen function. The speed at which we can write an entire screen full of pixels is actually quite slow, and that's what's slowing down our animation here. The flickering we're getting is actually the redrawing of the black screen. So each time it tries to clear the screen, it's actually taking quite a long time, and that's causing our animation to completely slow down and really be pretty much unusable at the moment. So if I simply take out that line and then redo that, upload that back to our Arduino, we should find how fast it can actually move the rectangle around. So let's see this coming up. And there you can see that the actual rectangle drawing function can actually run quite quickly. It's just purely that clearing the screen which was causing us a problem. So really we can't use that normal clear screen, draw a new frame method with this particular screen. There are ways around it, but we can't do that on this Arduino, which really involve creating a screen buffer where we can do lots of drawing into a buffered version of the screen and then simply blast that across as a series of individual bytes out to our screen. But for that to happen, we need quite a lot of storage space within our microcontroller, and the Arduino just isn't able to store a complete frame of animation inside itself. So we're going to have to work out a different way of doing this. And the way we can do it then is to actually simply overdraw. So instead of clearing the entire screen, we're simply going to clear the area which we're animating. So at the moment we've got this red square at this position X and Y. And really what we want to do is we want to, in effect, draw over the last place it was with black and then draw the new one in. So in fact we're rubbing out the old one and then drawing in the new one. So let's see if we can work out how to do that. So we know that this line of code here draws our square in the current position in red. So really we want some sort of version of that then. So if I copy that, we could put that up at the top here, and we could say up here, draw the square in its current position in black, then update the position and then draw it in red. And that should then give us a square bouncing around the screen. But really what we want to do is we want to make sure that our square stays on the screen as much as possible. So instead of putting in this line up here, really what we want to do is we want to have it down here. So just before we move the square, we want to then delete it so that our square stays on the screen as long as possible. So in fact, we delete it from the screen here, and then right after that, we then redraw the new position. Now to do that, obviously we've updated our X and Y coordinates at this point. So the X and Y here are actually the new positions. So we'll need to then remember what our old positions are. So we want to create two new parameters up here. So we're going to create two integers up here. And then before we update our values, we're going to say that old X, we'll set that equal to our X value, old Y equal to our Y value, and then down here we can simply then say so old X and old Y. So we make a note of where it is at the moment, we then update our values, we overdraw the old position, and we then redraw the new position. So let's see what that looks like on the Arduino. And there we have our red box animated around the screen. Now it's not a very good animation at the moment. We can see there that we're getting lots of lines and so on as we're redrawing. And if you think about it, really what's happening at the moment is we are drawing a rectangle in black, then drawing a rectangle in red. We are running this loop as fast as we can, and that then is causing it, we're actually seeing the building up of the pixel display happening as we animate our rectangle. So really we want to find out a few different ways of how we can combat this. If we look at what our code's actually spending its time doing at the moment, the block up here where it's doing the calculations, well in fact that's just doing a few additions and subtractions, so there's practically zero time involved in that block of code. And really all our code is doing is simply spending all of its time deleting a rectangle and drawing a rectangle. And if you think about it, that's why we're seeing this stippling effect happening, because we're viewing it as it's half drawn a black and half drawn a red and so on. So that really is why we're getting this problem. What we need to do is we need to slow the process down a bit, so that we actually have the red rectangle staying on screen for a little bit longer, so that our eye has time to register that and not then register the actual redrawing of these two shapes. So the simplest way we could do that would be to put a little delay after that. So let's say we put a 50 millisecond delay after we draw our red rectangle, and let's see what that looks like when we draw do the animation. So there we have the screen coming in now, and we can see that we're getting a much better effect. We still get a little bit of the stippling as we draw it, but again that's just one of the things you have to put up with this particular type of screen. The time it takes to actually draw that rectangle is not insignificant, so therefore you are going to get a little bit of this problem. But again, we can make that slightly better. So we now, of course, you will see as well that it has slowed down our animation. So our square is no longer moving as fast. But again, we can change that. If we then just simply, because we're now having a delay, we need to move it a little bit faster using our pixel values. So we could increase those two there to 3, and let's see what that does to it. So you can see we've now got our animation working a little bit faster. It is getting a little bit jerkier because of course we're making a bigger move per frame, and our frame rate, we do have quite a large delay there of 50 milliseconds. But again, that stippling effect, we can of course work on that as well. The amount of time it takes to draw each rectangle of course is very much related to the size of the rectangle. So if we reduce the size of the rectangle and then try that, we should now see that we get a better animation happening. So we now have a little box, or almost a dot now, animating around the screen, and it's not doing too bad. The stippling effect has gone because it's taking much less time to do the overwrite and then the redraw function, and we've got something sensible happening now. So we're starting to get to a usable system. So let's see if we can refine this a little bit further. We've currently got a delay at the end of our code loop, and that's going to be a fixed time delay. But really when we start to build up our code, we're going to have in this main loop lots more calculations and graphics and so on going on here. So really we don't want to have this fixed time delay at the end, because if we end up spending quite a lot of time up here, let's say we're spending 20 or 30 milliseconds up here, and then we just simply delay for 50 milliseconds, well that's going to slow our whole system down. What we want to try to get towards is a set frame rate. And if you think about any of the games you've done, this idea of a frame rate it should be something very familiar to you. So at the moment this is in effect giving us a frame rate, but as we increase the computational complexity of our code, that frame rate is going to drop and drop and drop. So really we want a way of almost enforcing a particular frame rate. So our code executes any extra time before the next frame needs to be drawn, that we will then have a pause for that, but we will let this code get as complicated as it wants, and our delay then will vary just to make sure that we hit our frame rate targets. So there's a function inside the Arduino which is called millis, and that really keeps a track of how long our code has been running. So what we can do is we can actually use that to then impose this frame rate. So what we need to do is we need to make a note of when the current frame has started. So whenever we come around to do the next frame, we will wait until it's the proper time for that one to start as well. So let's create a global variable here, and the millis function returns a long integer. So we need to create an unsigned long integer for our to remember this last frame rate. So we're going to create this last frame function, and we're going to set that equal to this millis function. And again, so this millis then, as I say, it returns back the number of milliseconds since the Arduino was last turned on. So inside our code then, really what we want to do is we want to say, okay, I know when the last frame ran, so this current frame shouldn't start until the next frame rate. So let's say we're going to set a frame rate of, just to make it easy, let's say we're going to set a frame rate of 50 frames per second. So that means that we have 20 milliseconds per frame. So really what we want to do here is we want to wait until the last frame had started 20 milliseconds ago. So we can use a simple while loop. So while, so this is our current time, so millis is our current time, minus our last frame start time. So while that is less than 20 milliseconds, so it's less than 20 milliseconds since we last ran the last frame, then we just sit in this loop. Once we've got to that next frame start time, we now want to log the time that this frame started at. So whenever we come back round again, we can wait until it's another 20 milliseconds since this frame started. So again, we'll say then, so last frame equal to millis. So what that should do for us now, that should impose upon our code a 50 frames per second rate. So what it will do now is it will do at most 50 frames per second. So if our code here takes a bit longer than 20 milliseconds to run, then that's fine. Our loop will simply say, okay, it's been longer than 20 milliseconds since we last ran a frame, so we'll run this frame immediately. So we can get, as our code gets more and more complex here, we can actually have our frame rate dropping off, but it will never get more than 50 frames per second. So we'll always have a little bit of time where our rectangle is on screen. So let's see what that does on our code then. So let's update that and see what happens. So just coming through to the Arduino, and there we see that, again, we are using a slower delay. So remember we had a delay of 50 milliseconds always at the end of our loop last time. Now we're saying, okay, we will have a delay of, it could be up to 20 milliseconds, because again, our code at the moment is very, very simple. But it means that we now have this set frame rate of 50 frames per second. And you can see our animation is starting to look pretty good. Okay, even though we are still moving at 3 pixels per frame, it's getting a reasonably smooth transition. And of course, because we're drawing a very small square, our actual stippling effect is not, we're not able to see that anymore. And again, this now means that as we build up the complexity of our code in this area here, our delay will modify itself just to keep this frame rate going. And again, by making sure that when we do need to move an object on the screen, we delete it and redraw it straight away, then of course the time between this object being redrawn, going through the rest of our code, of course there'll be lots of other things being redrawn and so on, we will actually then get that delay happening. And we should get some nice smoother animations taking place. So really this is the basis then of using one of these screens, or at least this is the way that I use these screens, especially when we come to do gaming where we want to have a particular frame rate to make sure that our game, as much as we can, doesn't speed up and slow down. And I say I'll be going through the Pong code in probably not this video, but the next video we'll go through that, and you'll see that we can actually create a nice sort of breakout clone using the screen. So this type of technique then of this rubbing out and redrawing to get our animation working, you start to use this now. Again, we're doing it here for what will eventually become sort of game animation, but any of your sort of control panels, perhaps you want to have a dial and so on. So the needle on the dial, you would do exactly the same effect, where you would calculate the new position of the needle, then overdraw the old position, and then redraw the new position, and so on. So this is the effect you need to use to create any sort of animations on these screens. Now that we have the basic idea of how to produce these animations, let's go a bit more complicated and see exactly what the screen's capable of. So I've rewritten a bit of code here that's going to bounce a number of rectangles around the screen, but let us have a look and see how well the screen's performing. So I've reworked it just slightly. We're going to use a rectangle class to represent each rectangle, which will just simply make it easier for us to have multiple rectangles bouncing around the screen. When we create our rectangle class, again we're in C++ here, so this is how we just define a class in C++. So we're defining a number of public attributes here. So we have the x and y coordinates, the last x and y coordinates where we drew the object, its vertical and horizontal speeds, a width and a height, and then a color value. We're going to randomize these, and the color value, we're going to randomize that. So we're going to work out an RGB value by just simply randomizing the R, G, and B variables. But we need to translate that into the correct format for the TFT. So it takes a 16-bit color value, which is made up from 5 bits of red, 6 bits of green, and 5 bits of blue. So we have our 16-bit number here, and you can see there how the various red, green, and blue bits are put into that. So that's all that this little line of code is doing here. It's masking off the bottom 3 bits of the R value, and then shifting it up into the top of that register. Then it's masking off the bottom 2 bits of the green and shifting that along a wee bit, and then masking off the bottom 3 bits of the blue, which gives us then this final RGB 16-bit value. When we instantiate a rectangle object, we will automatically randomize its position, its size, its speed, and its colors. That's all that's happening here. So we simply create a rectangle object, and it's instantly initialized to be a randomized size and speed on the screen. We then created 2 methods within this function. One is to actually move the rectangle, so we can simply ask a rectangle to move itself, and that's when it moves itself and then does its error or limit checking at the edges of the screen. And then our rendering function simply overdraws its old position, draws the rectangle in the new position, and then makes a note of where this last drawing position was. So when we come back around and re-render, we then overdraw the last position and then redraw the new position. So we're going to use an array of rectangles. So I'm saying here this is how many rectangles we're having, and then we'll be able to play with that a little bit. We've got the normal setup function. We just added the setup function then, so it's going to initialize each element in our array to be one of these rectangle objects. And then down here, the only extra thing we're doing really is I want to be able to see how fast each frame is being built. So we're going to have a frame display showing. I'm not going to display this every single frame, because otherwise we won't really be able to read the number. So really we're aiming for 50 frames per second here, and I'm going to redisplay the frame count or the frame time every 20 frames. So that'll be about half a second in effect. And that will let us actually see a number appearing and be able to read it. So I'm using a little timer here, and that timer is counting down every time we go through this program loop. So every 20th time through this loop, we will hit 0. So we reset the timer, and at that point, we simply overwrite the previous text, and then write in the new text, which of course is going to be the current milliseconds minus the last time a frame ran. So that will tell us how many milliseconds it was since the last time we ran a frame. And again, all of these functions, so that the TFT, fill rec, set cursor, text size, you'll find all of those detailed in that header file, and just simply work your way through there. And most of it is fairly self-explanatory, or at least you can have a bit of a play and see what's going on. So say we're basically sort of setting where the text cursor is. So again, that's relative to the top left corner of the screen. We're setting the text size, so that's just sort of double size. We're then setting the text color, and then we're printing out a value. Okay. So then we have our frame speed object there, and then all we're doing is we are looping through each of the rectangles in this rects array, asking it to move and then asking it to render itself. So that gives us our code here to have multiple rectangles or random rectangles bouncing on the screen, and we're going to have a bit of a play with various parameters to see how that affects our frame rate. So let's upload that into our Arduino and see what we get. So that's our code running at the moment, and you can see the time it takes to generate one frame is around about our 19 or 20 milliseconds. So that's pretty much our 50 frames per second. So at the moment, if we look at our code, that's using 10 rectangles, and the maximum size of our rectangles then is 25 pixels by 25 pixels. So again, we're letting them go up to that size. It doesn't mean we'll have all that size. But we can see there that if each frame is taking 19 or 20 milliseconds, and that's what we're trying to set it to, we are pretty much at the maximum of what we can do. So if I was to simply change the parameters here and double the number of rectangles that we have on screen, and let's upload that into our Arduino, this should have some sort of effect upon the amount of time it takes to generate one frame. So let's see what that does. So there we go. So we can see now that the rectangles have obviously slowed down a bit. And if you look at the frame time, it's taking around about 43 milliseconds to generate one frame. And of course, that's a lot slower than our target of 20 milliseconds. So you can see there that by having more rectangles, all of a sudden our system is no longer able to keep up that 50 frames per second. So dropping down to around about 40 milliseconds, so we're down to around about, what would that be? About 25 frames per second now. And again, if I was to up that value again, so let's up that now to, let's say, 30 rectangles, and upload that into our Arduino. That should again have another drastic effect upon us, and let's see what that brings our frame time down to, or up to. And you can see there, okay, it hasn't had such a massive effect, but again, that could be just simply because we're using random rectangle sizes here. But that number of rectangles, then again, it's dropped our frame rate down. So you can see now why some games, once you start to get lots and lots of things happening on the screen, it simply takes a longer time to draw those and calculate those, and so your frame rate will drop. So let's take that back then to 20. So again, so we're still going to be over our frame time. So it'll take us back down, hopefully once that's uploaded, to around about our 40 milliseconds per frame. So there we go. And let's see what else we can do to affect that. So we know that the number of objects we're animating has a drastic effect upon our speed. But let's now just take down the size. So at the moment we're randomizing the width and height of these between 5 pixels and 25 pixels each. So again, and we've already seen that the larger the object, the more pixels you have to turn on and off, so therefore the slower it generates. So let's take that down, let's take it down to 10, so between 5 and 10 pixels for each of our rectangles. And let's see how that affects then our frame rate. So there we go. And you can see by reducing that value, okay, we've got smaller rectangles, but you can see now that we're well inside our 50 frames per second target. So remember, we were targeting 20 milliseconds per frame, and we're now down about half that. So that should mean that with using these small rectangles, we should be able to have more of them on the screen. So let's say if we take up to, let's say, 40 and animate that. So that's now got 40 rectangles, and you can see we're just a little bit over our target of 20 milliseconds. So we're running here at probably around about sort of 45-ish frames per second. But we now do have 40 animated blocks running around the screen. So it looks like with this screen then, you can see that the number of objects affects it, and the size of the objects. And it looks more like the size has a bigger effect. So again, the more pixels we have to write every single time. Remember, every time we increase the size of an object, because we're having to overwrite it and then write it, we actually increase the number of pixels we have to draw by double that amount. So you can see why that has such a large effect upon it. So with these screens then, really what we're trying to do is keep the number of pixels that we have to write down to a minimum. So now that we have an idea of what the screen's capable of and what factors affect the speed at which it operates, we can really start designing our software to take that into account to make sure that we get what we want. So the drawing on these little serial screens, it is rather slow, so there is a big limitation on what we can do. But as you've seen, that doesn't stop us from doing some quite good things. And if I go across to what will be the subject of the next video, which is the little Pong or Breakout clone, we'll see that again. If I upload that, you'll see that we can actually do some fairly good stuff in this screen. Simply by making sure that we don't try and draw too big an area of a screen every single frame. We can drastically reduce the number of objects we have to draw and the speed at which we have to draw them, but by just thinking about what's going on. So again, part of the code is to work with the touch screen in the next one. So we're going to use the touch screen to move our bat. So there will be a calibration function, which I'm just going through here. So we're just calibrating the screen so that we can now, it does recognize where, and I can measure where we have put the cursor. And you can see here, so if you look at what's going on, you will see certain things happening. So if you look at the bat, you'll see that we don't actually redraw the bat every single frame. And you'll see that when the ball hits it, it sometimes knocks a bit out of the bat. So again, I'm simply redrawing the bat whenever I've noticed that it actually moved a reasonable amount of distance. So we still get a nice smooth animation, but it is actually only redrawing it if we've moved it more than 4 pixels from the last position. So therefore I don't have to redraw the bat every screen. Obviously the blocks, if you see them, those are not only drawn at the start of the code, and they're not redrawn at all. They're just simply removed whenever the block hits them. So you'll sometimes see that some of the edges of the blocks might get knocked out by the ball going over the top of them. So the only real thing which is being animated each frame is the ball itself. So if you think about it, all that's happening here is we've got one ball animated, a bat animating every sort of 2 or 3 frames, and that's all that's really happening here. The rest of it is just simply the actual code which works out what blocks have been hit and so on, and that bit of it the Arduino is really good at and doesn't take much time at all. So again, by reducing the number of pixels that we have to send out to our screen, we can create some nice little games. So that's been a quick overview of how we actually use these little SPI TFT screens. As I say, in the next video I'll be covering the Pong game, and we'll see then how we can use the touchscreen as an input device, and we'll be using that to move the bat around, and how we can then optimize the way in which we create our graphics to make sure that we get a nice fast-paced but smooth animation game working. Again, all of the code that I've been using in this lesson, or at least the final one where we have the multiple rectangles bouncing around, I'll make all of that available on my website. So if you follow the links in the description below, that will take you to the project page for this tutorial, and there you can both see exactly what's going on and download the Arduino file and get all that code. So, hope you're enjoying that. Look forward to seeing you then when we go through the Pong game, but have fun making things and coding. See you soon. Don't forget to visit the course pages for this project. There you'll be able to download the code for this lesson and get lots of extra hints and tips. You'll also get access to all my other programming, electronics and gaming projects. All the links are in the description below. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.